Hello everyone. Today we will study quantifiers. There are two types of quantifiers. Let me show you their symbol first. First one looks like upside down A. This symbol is called the universal quantifier. Universal quantifier means for all. Another quantifier looks like a right side left E. This is called existential quantifier. This is called an existential quantifier. And it means there exists something. First symbol looks like an upside down A. It's called a universal quantifier, and it means for all something. The other quantifier looks like a right side left E. This is called the existential quantifier. It means there exists something. Next, let me show you an example. It will make more sense to you. Let partitional functions s of x and f of x be defined as s of x represent that x can swing. Let f of x represent that x can fly. Let s of x represent s can swing. Let f of x represent s can fly. Then, based on this definition, for all x, s of x, it means the direct translation here is for all x, s can swing. That's the direct translation. For all x, s can swing. This means for all x, s can swing. If we use down-to-earth language, it means everyone can swing. If we use down-to-earth language, it also means everyone can swing. The direct translation says, for all x, s can swing. For all x, s can swing. It means everyone can swing. For all x, f of x, the direct translation means, if we use direct translation, for all x, f of x, it means for all x, s can fly. That's the direct translation. For all x, s can fly. If we use down-to-earth language, it means If we use down-to-earth language, this statement it also means everyone can fly. For all x, s can fly also means everyone can fly. Now, let's call it universal quantifier. Let's call it universal quantifier. It means for all. Let's call it universal quantifier. It means for all. Next, this symbol. What does this symbol means? This is called existential quantifier. It means there exists a x. There exists a x such that there exists x such that s can swing. This symbol means there exists x such that s can swing. S of x means s can swing. So there exists x such that x can swing. If we use down-to-earth language, it also means someone can swing. There exists x means someone can swing. If we use down-to-earth language, it means someone can swing. There exists x such that f of x. The direct translation says there exists a x there exists a x such that s can fly. That's the direct translation. There exists x such that s can fly. It also means what? If we use down-to-earth language, it also means someone can fly. There exists x, s can fly means someone can fly. If we use down-to-earth language, it means someone can fly. That's the direct translation, and that's the down-to-earth language. That's the language we use in our real life, and that's the direct translation for this statement. Next, let me introduce the domain of propositional function. The set of all objects that is under consideration. That's under consideration. The set of all objects under consideration is called the domain of a propositional function. The set of all objects under consideration is called the domain of the propositional function. For example, in the previous example, s of x represents s can swing. F of x represents X can fly. Assume their domain is the set of all students in our class. In the previous example, assume for these two propositional functions, their domain is the set of all students in our class. Then, for all x, s of x, it means what? We only consider students in our class. For all x, s of x, it means for all x in our class, S can swing. It means for all x in our class, that's our domain. We only consider people in our class. For all x in our class, S can swing. If we use down-to-earth language, it also means everyone in our class can swing. If we use down-to-earth language, it also means everyone in our class can swing. For all x, f of x, it means the direct translation says for all x in our class, S can fly. That's the direct translation. For all x in our class, S can fly. That's the direct translation. It also means, if we use down-to-earth language, it also means everyone in our class can fly. If we use down-to-earth language, it means everyone in our class can swing. It also means everyone in our class can swing. That's the down-to-earth language. There exists x, s of x. There exists x, s of x. That means there exists x in our class. There exists x in our class. If we use direct translation, this statement means there exists x in our class such that S can swing. That's the direct translation. There exists x in our class such that S can swing. If we use down-to-earth language, it also means someone in our class can swing. If we use down-to-earth language, this statement means someone in our class can swing. In real life, we use real-life language. We use down-to-earth language. This is direct translation. This is the direct translation. There exists x, f of x. What does it mean? If we use direct translation, it means there exists X in our class. Such that X can fly. That's the direct translation. There exists X in our class such that X can fly. That's the direct translation. If we use down-to-earth language, it also means that someone in our class can fly. That's the down-to-earth language. Next, let's look at a different example. Then a propositional function p of x represents s squared is greater or equal to x. Assume the domain is the set of all real numbers. Assume the domain is the set of all real numbers. Find the true values for each of the following statements. Find the true values for each of the following statements. First one. What's the true value for P of 2? What's the true value for P of 2? P of 2 represents 2 squared is greater than 2. P of 2 represents 2 squared is greater or equal to 2, which is true. We know that 2 squared is 4. 4 is greater or equal to 2. What's the true value for P of negative 3? What's the true value for P of negative 3? P of negative 3 represents P of negative 3 represents negative 3 squared is greater or equal to negative 3. We plug in negative 3 for x. Negative 3 squared is greater or equal to negative 3. Negative 3 squared is 9. 9 is greater or equal to negative 3. That's true. Next. What's the true value for f of 1 over 2? What's the true value for f of 1 over 2? For p of 1 over 2, sorry. What's the true value for p of 1 over 2? P of 1 over 2 represents half squared is greater or equal to half. P of half represents half squared is greater or equal to half. Is it true? Half squared is a quarter. A quarter is greater than or equal to half. That's false. What's the true value for P of 0? What's the true value for P of 0? P of 0 represents 0 squared is greater or equal to 0. We know that 0 squared actually equal to 0. So this statement is true. 0 squared equal to 0. This statement is true. Next. What's the true value for this statement? There exists x such that p of x. What's the true value for this statement? There exists x such that p of x. This statement means there exists x there exists x such that s squared is greater or equal to x. This statement means there exists x such that s squared is greater or equal to x. Is this true? Can we find x such that s squared is greater than x? We can see that here. 2 squared is greater or equal to 2. Negative 3 squared is greater or equal to negative 3. So there exists x such that s squared is greater than x. This statement is true. There exists such x. There exists such x. That satisfies that s squared is greater than x. So here, some x is greater than x. For some x, s squared is greater than x. This statement is true. There exists some x such that this statement is true. For example, 2, negative 3, and 0. So this is a true statement. How about next one? For all x, p of x. Is this statement true? For all x, p of x. Is this statement true? For all x, p of x. This statement means for all real number x, in the previous one, it should be there exists a real number x. The domain is all real number. So there exists a real number such that there exists a real number x such that s squared is greater or equal to x. So number 6 says, for all real number x, s squared is greater or equal to x. This statement means for all real number x, s squared is greater than x. Is this true? Not for all number. Not for all real number. For example, half. If I plug in half, this statement is false. So this statement is not true for all. It's not true for all real number. This is a false statement. This statement is not true for all x. So this is a false statement. Let's continue. In the previous example, the propositional function p of x represents s squared is greater or equal to x. If we change the domain to the set of all positive integers, if we change the domain to the set of all positive integers, then determine the true value for there exists x, p of x, and for all x, p of x. If we change the domain to the set of all positive integers, then determine the true value for these two statements. There exists x, p of x, for all x, p of x. There exists x, p of x. Is this true or false? This statement now means there exists a positive integer x such that s squared is greater or equal to x. Now this means there exists a positive integer x such that s squared is greater or equal to x. Is this statement true? Can we find an x that x squared is greater or equal to x? We can easily see that if we plug in 2, 2 is a positive integer. That makes this statement true. So there exists a positive integer that makes this statement true. This is a true statement. It's a true statement because number 2 is in the domain and p of 2 is true. This statement is true for some x in the domain. So this statement is true. How about this statement? For all x, p of x. For all x, p of x, it means for all positive integer x, for all positive integer x, s squared is greater or equal to x. This statement means for all positive integer x, s squared is greater or equal to x. Is this true? Is this statement true for every x? Is this statement true for every x? When we plug in 1, 1 squared is greater or equal to 1, that's true. When we plug in 2, 2 squared is greater than 2, that's true. 3 squared is greater than 3, that's true. It looks like this statement is true for every x. Since p of x is true for every x in the domain, the statement for all x, p of x is a true statement. Next, let's consider the previous example again. In the previous example, the propositional statement p of x represents s squared is greater or equal to x. If we change the domain to the interval, from 0 to 1, That means all real number between 0 and 1. If we change the domain to the interval from 0 to 1, this interval means all real numbers between 0 and 1. This interval means all real numbers between 0 and 1. If we change the domain to the interval from 0 to 1, then determine the true value for there exists x p of x, and for all x p of x. Determine the true value for there exists x p of x, and for all x p of x. So here, there exists x p of x. That means there exists a x. There exists a x between 0 and 1. This symbol means it's between 0 and 1. There exists x between 0 and 1, such that x squared is greater or equal to x. There exists x between 0 and 1 such that x squared is greater or equal to x. Let's try some examples. If I plug in half, half square is a quarter. Quarter is not greater or equal to half. If I plug in 1/3, that's 1/9. That's not greater or equal to 1/3. The larger denominator, the smaller it is. Since when we square a fraction will make the denominator larger, this statement, we can't find any x that can make this statement true. Here we cannot find any x in this domain that can make this statement true. There's no number between 0 and 1 can make this statement true. So, since no x can make this statement true, this statement, there exists x such that p of x is false. It's a false statement. Because for all x because no x between 0 and 1 can make this statement x squared greater or equal to x true. Because no x between 0 and 1 can make x squared greater or equal to x true. Since no x can make it true, this statement says there is x which can make this statement true. The entire statement is false because this statement says there exists such x, but eventually we'll find out there's no such x can make this statement true. So this is a false statement. This is a false statement. No x can make this statement true. Next one, for all x p of x. This means for all x between 0 and 1, x squared is greater or equal to x. This is obviously not true because half is between 0 and 1, but half squared is not greater than half. This is false statement. It's a false statement. Because, for example, half is between 0 and 1. Half is between 0 and 1, but p of half says half square, p of half says half square is greater or equal to half is false. If one of x make this statement false, this statement will be false. So this is a false statement. If one of an x make this statement p of x false, then the entire statement is false. Next, let's make a conclusion for true values of quantified statements. First one, the statement for all x, p of x. This statement is true if the statement p of x is true for all x in the domain. This statement for all x, p of x is true if p of x is true for every x in the domain. This statement for all x, p of x is false this statement for all x, p of x is false if p of x is false for one of x, for at least one x in the domain. One of x means at least one x. This statement for all x, p of x is false if the statement p of x is false for at least one x in the domain. Next, this statement, there exists x, p of x. This statement is true if the statement p of x is true for at least one x in the domain. This symbol means there exists x such that p of x. If this statement p of x is true for at least one x, that means there exists such x. So the entire statement is true. This statement, there exists x, p of x. This statement is false if p of x is false for every x in the domain. This statement, there exists x, p of x. This statement is false if p of x is false for every x in the domain. If one of x makes p of x true, then this statement will be true. So keep in mind that this statement for all x, p of x, this statement is true if p of x is true for all x or for every x in the domain. All x, every x is the same thing. This statement for all x, p of x is true if p of x is true for every x in the domain. So if for every x, p of x is true, then this statement for all x, p of x will be true. But if one of x make p of x false, then this statement is false because it's not for all x. If one of x make p of x false, then this statement is not true because it's not for all x. There exists x, p of x. If p of x is true for at least one x, that means one of x make this statement true. That means there exists one x. If at least one x make this statement true, that means there exists one x. So this statement will be true. But if every x make this statement false, then there exists x, p of x will be false. Otherwise, if one of x make this statement true, this will be true. So that's a rule for quantified statements. That's how to determine true value for quantified statements. That's the rule. Keep it in mind. Next, Based on the above rules, if p of x is a propositional function, with domain s1, s2, x3, and so on. Assume p of x is a propositional function with domain s1, x3, x1, s2, x3, and so on. Then the statement for all x, p of x is equivalent to p of s1 and p of s2 and p of s3 and so on. This statement for all x, p of x is equivalent to p of s1, p of s2, p of s3, and so on. That means if this statement is true, that means p of s1 must be true, p of s2 must be true, p of s3 must be true, and so on. This statement says for all x, p of x. If this statement is true, that means this statement must be true for every x, which means p of s1 must be true, p of s2 must be true, p of s3 must be true, and so on. If one of x makes this statement false, then the entire statement will be false. Because for n, if one of them is false, the entire statement is false. When they are all true, this statement is true. If one of them is false, this statement is false. So they are equivalent. For all x, p of x is equivalent to p of s1 and p of s2 and p of s3 and so on. The statement there exists x, p of x. The statement there exists x, p of x. This is equivalent to p of s1 or p of s2 or p of x3 or everything else. This means if p of x is true for one of x, then the entire statement will be true. If p of x is true for one of x, then the entire statement will be true. This is the same thing. There exists x. If p of x is true for one of x, this statement is true. So these two statements, they are equivalent. This statement for all x, p of x is equivalent to p of s1 and p of s2 and p of s3. And this statement, there exists x, p of x is equivalent to p of s1 or p of s2 or p of s3 and so on. So keep this idea in mind. Next, let's look at the negations of quantified statements. How do we negate a quantified statement? How do we negate a quantified statement? Let p of x be a propositional function with domain s1, s2, x3, and so on. How do we negate the statement for all x, p of x? According to the previous rule, for all x, p of x means p of s1 and p of s2 and p of x3 and so on. When we distribute not, we apply De Morgan's law. The sign in operation in the middle will be switched. When we distribute negation, operation in the middle will be switched. So it become not P of S1 or not P of S2, n become or not P of X3 or so on. When we distribute negation, operation will be switched. Operation will be switched. When we have or here, consider not P is a new statement. Consider that's a new statement. We have a statement or a statement or a statement. That's the existential quantifier makes X such that not P of X. We consider not P as one statement, as one propositional function. So every function here is the same. So not P, there exists X such that not P of X. So keep in mind that not for all X, P of X, that means there exists X, not P of X. That means if we bring negation inside a quantifier, the quantifier will be switched. If we bring a negation into the quantifier, the quantifier will be switched. For all X become there exists X. And similarly, for the other one, negation of there exists X such that P of X. So rewrite there exists X P of X first using the previous formula. There exists X P of X, that means P of S1 or P of S2 or P of S3 or so on. If we distribute negation, operation will be switched or become n. So that's not P of S1 and not P of S2 and not P of X3 and so on. Now we consider not P as a new function. We consider not P as a new function. The relation in the middle is n, so I can write it as for all X, not P of X. If we consider not P as a new function, for all X, and the relation here is n, so we can write for all X, not P of X. So keep it in mind that the negation of there exists X, P of X is that's equivalent to for all X, not P of X. So the negation of there exists X, P of X is equivalent to for all X, not Px. When we bring negation inside into a quantifier, quantifier will be switched. There exists X become for all X, and for all X become there exists X when we bring negation inside. Next, let's try more problems. For each of the following statements, assume the domain is the set of all integers. Determine the true value for each of the following statements. First one, there exists X such that X squared is greater than X. There exists X such that X squared is greater than X. If this statement is true for one of X, then this will be true. But if it's not true for all X, it will be false. There exists X. Can we find X that make this statement true? Can we find X then make x squared greater than x. Can we find x? Then make x squared greater than x. If y s is equal to 2, then s squared equal to 4, which is greater than 2. Hence, s squared is greater than x. So if this statement is true for 1x, the entire statement will be true. So the answer is true. If this statement s squared greater than x is true for 1 over x, the entire statement will be true. Next, for all x squared is greater than x. Is this statement true for every x? We know it's true for 1x. Is this true for every x? We know this statement is true for at least 1x. Is this true for every x? If this statement is true for every x, then this quantified statement will be true. Otherwise, it will be false. Is this true for every x? What if s is 0? When s is 0, what do we have? When s is 0, then s squared is 0 squared, which is also 0. So s squared is not greater than x. In this case, s squared is not greater than x. If s squared is 0, 0 is not greater than 0. So s squared is not greater than x. If I can find 1x, make this statement false, then that means it's not true for every x. Then this quantified statement is false. Now let's make one note here. This example here that make this statement false is called a counterexample. Keep this in mind. The example which make the quantified statement for all x, p of x false. It's called a counterexample. It's called a counterexample. The example that make the statement for all x, p of x false is called a counterexample. Counterexample. Next. For all x, s squared is greater or equal to x. For all x, s squared is greater or equal to x. If we plug in 1, that's true. Plug in 2, that's true. Plug in 3, that's true. Plug in 0, that's true. Plug in -1, it's true. Plug in -2 is true. It looks like it's true for all x. Can we prove it? It looks like it's true for all x, but how to explain it? This is true for all x. How to explain it? So let me show you a way to explain this. Why this is true? Let me show you one way to explain why this is true. Here, domain of x is the set of all integers. That means s could be 0, 1, 2, 3, 4, and so on. On the other side, it could be -1, -2, -3, and so on. Let's consider two cases. S could be either greater or equal to 1, or S could be less or equal to 0. Consider two cases. S could be either greater or equal to 1, or S could be less or equal to 0. So for all integers x, either s is greater or equal to 1, or x is less or equal to 0. if, case 1, if s is greater or equal to 1, then s is obviously positive. If s is greater or equal to 1, then s is positive. S is greater or equal to 1. If I multiply both sides by x, if I multiply both sides by a positive number, x times s is greater than equal to 1 times x. Since s is positive number, if I multiply both sides of an inequality by a positive number, the inequality sign stays the same. So we have x squared greater or equal to x. That's case 1. If s is greater or equal to 1, we prove x squared is greater or equal to x. Or if x is less or equal to 0. Or if s is less or equal to 0, then if s is less or equal to 0, I can say 0 is greater or equal to x. If x is less or equal to 0, then we can say 0 is greater or equal to x. Since x squared is always greater or equal to 0, and we know that 0 is greater or equal to x. Since x squared is always greater or equal to 0, when we square a number, it's always positive, it's always non-negative. X squared is always greater or equal to 0, and we know that 0 is greater or equal to x. By transitive property, if s is greater than 0, 0 is greater than x, then s squared is greater than x. If s squared is greater than 0, 0 is greater than x, s squared is greater than x. So s squared is greater or equal to x. That's case 2. If x is less than 0, we can also prove that x squared is greater or equal to x. So in both cases, we have the same conclusion. That's why this statement is true for every x. And that's how we prove it. Next example. There exists x such that s is equal to 2 over x. Can we find one x that make s equal to 2 over x? Can we? When s is 1, that's not true. When s is 2, that's not true. It looks like no matter what you plug in, you can never make it true. It's not true for all x. When s is 0, that's undefined. When s is 3, that's not true. 4, that's not true. It looks like no x can make it true. We can't find any x to make it true. This statement looks like it's false. Can we prove it? Can we prove this statement is false? So let's do this. Assume there exists such x. Assume it's true. We try to see that's impossible. Assume there exists an integer x because the domain is integer. Our domain is the set of all integers. Assume there exists an integer x such that s is 2 over x. We try to show that that's impossible. Assume there exists such x. We try to show that's impossible. Assume there exists such x. Then we have x squared. Assume we have such x such that s equal to 2 over x. Then if I multiply both sides by x, I can make s squared equal to 2. I can multiply both sides by x, make s squared equal to 2. If I make s squared equal to 2 and solve an equation for x, what do we get? Which x can make s squared equal to 2? The only possibility is s either equal to plus or minus not equal to 2. But they are not integers. X must be integer. That's false. S must be an integer, but this is not integer. That's called a contradiction. We assume there exists such integer x such that s equal to 2 over x. But eventually we find out there is x, but this x is not integer. So that's impossible. Since we cannot find such x, that means there doesn't exist any x that can make x equal to 2 over x. this statement is false. There doesn't exist any x that can make x equal to 2 over x. If we cannot find any x that can make this statement true, it will be false. Next, for all x, x plus 1 is greater than x minus 1. Is this true? Let's try some numbers. If I plug in 0, 0 plus 1 is greater than 0 minus 1. 0 plus 1 is 1. 0 minus 1 is negative 1. 1 is greater than negative 1. That's true. If I plug in 1, 1 plus 1 is 2. 1 minus 1 is 0. 2 is greater than 0. It's true. If I plug in 2, I got 3 greater than 1. That's true. If I plug in 100, I got 101 is greater than 99. It's always looks like this statement is always true. Can we prove it? It looks like this statement is always true. Can we prove it? Can we give a proof? We know that x plus 1 is always greater than x. When we add 1 to x, it's always greater than x itself. And x is always greater than x minus 1. When we subtract 1 from x, it's always less than x. So by transitive property, since x plus 1 is greater than x is greater than x minus 1, then x plus 1 is greater than x minus 1. This is true for all x. Next, there exists x such that x plus 1 equal to 1 over x plus 1. Can we find 1x that make this statement true? If we can find 1x that make this statement true, it will be true. It says there exists x such that. If we can find 1x that make this statement true, it will be true. But if we cannot find any x to make this true, this statement will be false. Can we find any x to make this statement true? Let's try. If I plug in 1, I get 1 plus 1 is 2. 1 over 1 plus 1 is half. 2 equal to half. That's not true. Can we try a different example? What if I try 0? What if I try 0? 0 plus 1 is 1. 1 over 0 plus 1 is also 1. I get 1 equal to 1. That's true. So if I find 1x that make this statement true, this statement will be true. There exists such x. There exists such x that can make this statement true. So let x equal to 0. Then the left hand side equal to 0 plus 1 equal to 1. Right hand side equal to 1 over 0 plus 1. That's 1 over 1, which is also 1. So left hand side equal to right hand side when x equal to 0. If 1x make this statement true, it will be true. There exists such x. That means there exists such x that can make this statement true. Next, there exists x such that 2x equal to 7. There exists x such that 2x equal to 7. Is this statement true? There exists x such that 2x equal to 7. Is this statement true? Can we find an x which make this statement true? Can we find x which make this statement true? If I plug in 1, I get 2 here. 2 is not 7. If I plug in 2, I get 4 here. 4 is not 7. If I plug in 3, I get 6. 6 is not 7. If I plug in 4, I get 8. 8 is not 7. It looks like it never reaches 7. 2 times any integer can never be 7. So it looks like the statement is false. Can we prove it? Can we prove it? So same thing. Try to prove by contradiction. Assume there exists such x. We try to see that's impossible. Assume there exists such integer x. We try to see that's impossible. Assume there exists an integer x such that 2x equal to 7. Assume there exists x such that 2x equal to 7. Then, if I solve this equation for x equal to 7 over 2, we know that 7 over 2 is no integer. So that's impossible because x must be an integer. Assume there exists integer x, but we find out x is no integer. Assuming there exists such x, we find something impossible. That means there does not exist any x that can make this statement true. If we cannot find any x that can make this statement true, this statement will be false. Next, for all x, square root of x squared equal to x. For all x, square root of x squared equal to x. Is this statement true for all x? For all x, square root of x squared equal to x. Is this statement true for all x? If it's true for all x, if this statement is true for all x, then this statement is true. This quantified statement will be true. But if this statement is not true for one of an x, then the statement will be false. Let's try. If I plug in 1, 1 squared is 1. Square root of 1 is 1. If I plug in 2, 2 squared is 4. Square root of 4 is 2. It looks like it's true for positive number. How about negative number? If I plug in negative 1, negative 1 squared is 1. Square root of 1 is 1. That doesn't equal to x, so it's false. We can show this by give a counter example. The example that makes this statement false is called counter example. So let s equal to negative 1. Then square root of x squared equal to square root of negative 1 squared. Negative 1 squared is 1. Square root of 1 is 1. Then we can see that square root of x squared doesn't equal to x. Square root of x squared is positive 1. S is negative 1. They are not the same. The example that makes this statement false is called counter example. For the statement for all x, p of x, the example that makes this statement false is called counter example. So x equal to negative 1 is a counter example for this statement. Next, for all x, if s is greater or equal to 0, then square root of x squared equal to x. For all x, if s is greater or equal to 0, then square root of x squared equal to x. Now for positive number, this statement will be true. Let's give an explanation. If s is greater or equal to 0, then square root of x squared is always absolute value of x. If s is greater or equal to 0, absolute value of x is the same as x. So that's true for all x. Next one. There exists x such that if s is less than 0, then x equal to s plus 1. There exists x such that if s is less than 0, then s equal to s plus 1. Can we find x that make this statement true? This one looks weird. This one looks weird. Can we find one x that make this statement true? Let's try. Let's try some numbers. If I let s equal to 1, then s less than 0 is false. 1 less than 0 is false. And s equal to s plus 1 is true or false. If s is 1, 1 equal to 1 plus 1, 1 equal to 2 is false. It's also false. If s is 1, 1 less than 0 is false. If s is 1, 1 equal to 1 plus 1, 1 plus 1 is 2. 1 equal to 2 is also false. Hence, this statement x less than 0 implies s equal to x plus 1 is equivalent to false implies false. According to the truth table, false implies false is true. According to the truth table, false implies false is true. Since I can find one x that make this statement true, that means there exists such x that satisfies condition, then this is a true statement. This is a true statement.